we're going to talk projections. I'm going to get a tablet soon, I promise. So projection vectors are, I'm going to show you a visualization for this so it's easy to understand what a projection is, because that's something I struggled with a little bit while learning it. But what a projection is let's say you have projection of vector u, and this is vector v. So you've projection of u onto v, and keep in mind this is the format of the projection. You're going to have a subscript of whatever vector you're projecting onto, and you're going to have the big guy right here, the non-subscript vector name for the one that you're projecting onto the smaller vector. So what that means is basically here, vector, the red one, is going to draw an arrow. Let's say we slide this vector down and down and down until it is parallel or goes into the same direction as vector v. And keep in mind, there's not 4 vectors here. I'm just drawing this to show you that we're kind of dragging this red vector or vector u down this perpendicular line that it makes with v so that it becomes parallel with vector v. So projections, they basically create a parallel line. U becomes parallel with v, but keep in mind u does not keep the same magnitude, so u does not keep the same. I feel like I have to. Projection u onto v does not keep the same magnitude as u. So u will actually get shorter. Not u, but the vector u will get shorter as you drag it down this perpendicular line that it makes. So let's draw another example of this. So you have a vector that looks like this. Red, and let's do green again. Well, we can actually draw it like this. Now, this is the hard part right here of understanding what projections are. Let's erase this previous one as a distraction. But what a projection is let's draw an imaginary dotted parallel line along with this vector via v, and let's call this vector u. So again, this is going to be projection of u onto v. Here's the thing about projections. They can be longer than the vector you're projecting onto. So, well, the vector u can drag down like this until it is parallel with v. So basically what a projection is, makes the big guy up here project onto subscript vector. And this is what it looks like. You're going to create a perpendicular line with the vector you're projecting onto that reaches to the tip of the vector you're projecting. So this is what I did. I drew a perpendicular line right here that will make it so, that will make it so that the vector you're projecting, this one you're projecting, slide down this perpendicular line till it's parallel to the vector that you're projecting onto. So this hard to visualize a little bit, but this also works in 3D. So keep in mind, if you're taking calculus 3 for these vectors, this will apply in the 3D, because the formula for the projection, and this is actually how you get this new vector right here. Let's call this new vector the projection. But this new vector right here, let's call it projection, can be solved or can be found by this little formula right here using dot product. So u dot v, and this is the absolute value symbols. Actually, I don't think you need absolute. No, these are not absolute value symbols. U dot v over v dot v. That's a v dot v. Put that in parentheses. Times vector v. So when you find these two dot products, you're going to get whole numbers. You're going to get real numbers, not whole numbers. I don't know, whatever. Decimals, fractions. You're going to get some scalar value. That's what it's called. And these scalar values inside of here are going to be multiplied by vector v. Now here's the thing about that. This projection is going to give you a vector. It's not going to give you a scalar value. And that vector is going to be this projection right here. The one that is parallel with vector v. So I'll give you an example of this actually. And I'll draw a picture after I do the problem. Let's keep this up. I can leave the formula here. So let's say we want to find the projection of u onto v, and not u is equal to. U is 5, 2, and 3. And v is 6, -3, and 10 or something. Well, let's find the dot product first of u and v. That's the top of the formula here. So u dot v is equal to the corresponding points, 5 times 6 plus y values, these are corresponding points, 2 times negative 3 plus 3 times 10. All this is equal to 30 plus negative 6 plus 30, which this is equal to 54. So we have u dot v now. We have to find v dot v. So v dot v is 6 times 6 plus 3 times negative 3, which is just 3 times 3, because the number will turn positive, and 10 times 10. So this is 36 plus 9 plus 100 is 145. So we're actually going to get a fraction here. So let's put an equal sign. So we'll have 54 at the top and 145 at the bottom for the dot products of this calculation. And then we're going to have times vector v. And vector v is 6, negative 3, 10. So once we have these values, let me double check this actually. I'm going to put this in my calc. 36 times 9 times 100, not times, sorry, plus equals 145. Yep, that's right. So if we just distribute this scalar along every single number inside of this vector, you're going to get the projection. And I don't think I can draw a three-dimensional vector here, but the rules still apply. Let's just say that let's just visualize that this is the 6 and then this is the vector, let's say, I don't know, something along here. So this vector right here, vector v, we're trying to project u onto v. Now here's the thing, v doesn't even have to be going in the same direction. Just draw a dotted line for anything that is in the path of v, right? And then all you have to do is project u onto this dotted line. So this will be our resulting vector. Now the thing about this is the reason why we multiply a scalar by the vector v that we're projecting onto is because when you multiply a vector by any scalar, so let's actually erase all this. So when you multiply a vector by any scalar, you're going to get a new vector that is parallel to the vector you multiplied by. So let's say we have vector p or something, I don't know, p. And if you multiply p by 5, it will still be parallel to the original vector p. And let's give you an example. Let's say p is equal to, or the vector p is 3, 2, 10. We multiply p by 5, vector p by 5, and then we'll get 15, 10, and 50. This is still parallel to the previous vector. And I can get into that reasoning in another video, but just keep in mind that when you multiply any vector by a scalar, it will still be parallel. So that is why we find a scalar inside of this projection formula, so that we can get a parallel vector for this guy right here. Actually, you know what? I'll get into why it is. So I guess this is not going to be a practice problem video. This is just going to be a reasoning video. I think I'll make more of those actually, because I feel like understanding the math is better than just knowing how to do it. So let's say we have a vector, this guy right here. And the components of the vector are 3 in the x direction and y in the 4 in the y direction. Now 5 here is going to be the magnitude of the vector because this is the hypotenuse of what it looks like is a triangle. Now keep in mind, even if you multiply the components of a Pythagorean triple, right? The Pythagorean triple 3, 4, 5. Even if you multiply the components here by 5, the value of the hypotenuse will also get multiplied by 5. And what I mean by that is, let's actually do 2 because that's easier to understand. So let's multiply 3 by 2 equal to 6. 4 by 2 is equal to 8. Oh, I already wrote 8 too early. 8. If we use the Pythagorean theorem here, and let's say we have a new vector whose x component is 6 and y component is 8. If we use the Pythagorean theorem here, we do 36 or 6 squared plus 8 squared, we still get 10 in the final one. And what's 10? 10 is 5 times 2. And we multiplied the previous magnitude of the vector, the previous components, sorry, by 2. The magnitude also gets multiplied by 2. So that's the thing about triangles. Well, you'll learn that, you probably know this in about if you took trig. But when you multiply any vector by a scalar, it will give you a parallel vector because of triangles. So this triangle right here, even though it has different components, the ratio between the components are still the same. And you could try this with any Pythagorean triple. You can try this with 5, 12, and 13. If you multiply 5, 12, and 13 by any number, the hypotenuse and the, let's say you multiply all this by 3, the hypotenuse and the legs of this triangle will all get multiplied by 3. And this will turn out to be 39. So let's say you have a triangle where the side lengths are 50 and 36. The hypotenuse will turn out to be 39. And since the ratios are the same, the angle of this vector along this x-axis will be the same. That's when you multiply a vector by any scalar, it will be parallel. Now, let's move on to the next topic of today, the scalar. Way easier to scalar projection. Way easier to calculate the scalar of projection of u onto v. So it's still u onto v with the little subscripts is equal to u dot v over the magnitude of v. So this one's not that hard. Let's use the previous one, 5.2. I think it was 5.28 or something. I don't know. I'll just make up a new one. And we have v of 2, 3, -4. So let's find the magnitude of v first. Magnitude of vector v is equal to square root of 2 squared plus 3 squared plus 4 squared. And then let's put that into the calculator. You know what? I'm not doing that. That's a very large decimal number. Let's go with 29, square root of 29. So the square root of 29 is the magnitude of v. So we have this bottom value here. Let's do u dot v. So u dot v is equal to 5 times 2 plus 5 times 2 is the corresponding points for the dot product. So 5 times 2 plus 2 times 3 plus 8 times -4. What do we get? We get 10 plus 6 minus 32, which is equal to -16. So now that we have -16 at the top, divided by square root of 29, well, let's just say this is the answer here. And what the scalar of this is, what the scalar actually is the scalar projection. What it actually is the magnitude of the projected vector. So let's draw it out. Vector this. Let's actually make a vector in the opposite direction for practice sake. But draw a parallel line, perpendicular line, sorry. And the new vector, say this is u, and let's say this is v. This projection vector, and let's draw this as white. This projection vector magnitude is equal to this. So this new guy right here is just calculated by this formula right here. And the projection and the actual directions and components of the vector are calculated by this up here. So that's it for projections and scalars of projections. If you have any questions, put it down in the comment section. It's a pretty hard concept to grasp,